I found that the next main portion of the project involved the design of the ALU on the right side of the bus. So in order for for subtraction to occur, so for the subtraction of the B output from A, so A minus B to occur, we would need to turn B into a 2's complement because there is no subtraction with binary numbers. We can add negative numbers. So to convert from decimal to to convert from binary to 2's complement, you have to first invert the binary values you have. So for that, I have this inverter here, but it is it's almost like a tri-state inverter, control inverter, so it has an enable. So I basically said that when subtract is enabled, so when the add subtract is 0, when that value is inverted, and when it's 1, that enables this controlled inverter to invert the inputs and send them into the full adders here. We'll discuss in a sec. But if this were 1 for addition, these values would just go to a tri-state buffer, and the values B would just go through and to the full adders, where they would be added to 0 to just get the same B value, because we don't want to, for addition, we don't need to change to 2's complement. So back to subtraction. We have the full adders cascaded as before, and originally I had added 1 here. I had 0, 0, 0, 1, and I had used that to add. But I realized you can also just add by having a 1 as the carry input. So when we subtract, we have a 1 as the carry input, and that allows us to add 1 to whatever this value is to get out the 2's complement form, essentially. So say we had 1, so in 2's complement, basically what we would do would be invert this, so we would have 1, 1, 0, and then we would get, and if we added 1, we would get 1, 1, 1, 1, as we can see here, and that corresponds to, if we had negative 2 to the third, we have negative 8 here. Then we add to that 2 to the second, 4, 2 to the first, 2, 2 to the 0, so if we had 7 to negative 8, we would get negative 1. So that allows us to subtract 1 from A by adding negative 1. And then, this is the first part. We go to the actual ALU, where we have the B from before, whether it's the 2's complement or the regular B, as an input, and then the A as an input, and we have them cascaded with full adders, as we have seen before, to produce a 4-bit output. And then we can see that at work right here. So I put in the A register. And as you can see here, this is an example. I'm unsure why, as when this A register is enabled, it is a rising edge, it's not writing into the output. And I'm unsure why. So then we take the output from register A, becomes an input of the ALU. We send the output of register B through that 2's complement converter that we made, the add subtract input. That becomes an input, and then it outputs the subtracted value in this case. And then once the enable ALU is activated, it will write that value to the bus.